Covalent Bonding, Part 1, Ionic Bonding Review, and Covalent Bonding Intro. We're going to talk about two-dimensional structural formulas, or Lewis structures, and single, double, and triple covalent bonds. In this video, we're going to be using electron dot structures. Now, what we can do for electron dot structures is write the model for the atom that represents the number of valence electrons. We're going to do this for representative elements, so let's do a quick review of that. If we go across the periodic table, the representative elements are the first two columns and the last six columns. The number of valence electrons is the number of outermost s and p electrons. The s electrons fill in the outside of these atoms, and the p electrons fill in the outside of these atoms. If we go across the periodic table, everything in this first column will have one valence electron. In the second column, they'll have two valence electrons. That's because in the first column they end with S1. In the second column, they all end with S2 if we write electron configurations. As we go across the periodic table, elements in this column end with S2P1, three valence electrons. The number of valence electrons is indicated in red. Elements in this column have four valence electrons. They end with S2P2 in their outermost energy level. Five valence electrons for these elements, S2P3. Six valence electrons for these elements, S2P4. Seven valence electrons, S2P5. And finally, noble gases have eight valence electrons, S2P6. Remember that when atoms have eight valence electrons, or an octet of valence electrons, that makes them stable. So atoms will change their electron configuration so that they have eight valence electrons. All right, so we represent the number of valence electrons with dots. So just a quick review of writing electron dot structures, and we're going to take a look at the representative elements out of groups 1, 2, and 13 through 18. Now remember, the number of valence electrons is 1, 2, 3, 4, 5, 6, 7, 8 as we progress across those groups. So using period 3 elements as an example, we can see that the electron dot structure for sodium would have one valence electron, so we give it one dot. For magnesium, it would have two valence electrons. It's in group 2. And it would have two dots. We put those dots as far apart as possible because, remember, electrons repel electrons. Like charges repel. That's part of the law of electrostatics. All right, as we progress with four dots, elements in group 14, or rather, I guess we skipped group 13. They have three dots, and then four dots. Group 15 will have five valence electrons, five dots, then six dots. And we want to keep the electrons as far apart as possible, so when we have two pairs, we're going to keep those pairs across from each other. And then seven dots and eight dots as we progress across the periodic table. Now, where the dots go really just depends on the fact that we keep electrons as far apart as we can from other electrons. Separate the dots as much as we can. So if there's a single dot, we could put it on the top or the left or the bottom or the right. It doesn't really matter. If there's two dots, we could put them left, right, or we could write two dots on the top and on the bottom. With three dots, we could go left, right, top. We could go top, left, bottom. We could put those dots left, bottom, right. And we could put those dots right, bottom, right, and top. We just, again, want to keep the dots as far apart as possible, and all four of those different choices will work. If there's four dots, we'll have one dot on each side of the symbol. When we have five dots, we could put the single pair in that five dot configuration with the two electrons on the top, the pair on the top. We could put the pair of electrons on the right and the single electrons on the top and the right. I'm sorry, the pair on the left and the single electrons on the top, on the right, and on the bottom. We could put the pair on the bottom and the single electrons left, right, and top. And finally, we could put the pair on the right with the single electrons top, left, and bottom. When you have two pairs of electrons, they can either go left and right, or we can put the two pairs on the top and on the bottom with the single electrons on the left side. When we have three pairs of electrons, the single electron can be itself alone on the right, or we can put the single electron on the top and then fill in the pairs in the other spots. And that would be 7 valence electrons total. We can put the single electron on the left and fill in the other sides of the symbol with pairs, or we can put the single electron on the bottom and fill in the other sides with pairs. Again, it doesn't really matter. We just want to make sure electrons are as far apart as possible. When you have 8 valence electrons, we just have 4 pairs around the symbol. Now remember, the symbol stands for the nucleus of the atom and all of the electrons that are on inner energy levels, or what we would call core electrons. The dots represent the valence electrons. All right, so a quick review of ionic bonding. For ionic bonding, we say that valence electrons are transferred. Let's take a look at an example with sodium chloride, or NaCl. That's the chemical formula. One way to represent the ionic bonding is to use the crisscross and reduce model. What we do is identify that sodium is in the column where 1 plus ions tend to form, and chlorine is in the column where 1 minus ions tend to form. So for the representative elements, sodium is in that 1 plus column, and chlorine is in that 1 minus column. And representative elements are all very predictable. We can see that the charges for those 2 columns and these 6 columns are identified on this periodic table. Elements in the middle part of the table, of course, we have to determine by experiment, and many of those are written up here on the top of the ion sheet. So we just move that one there, and we get that chemical formula. That's one way we could represent the ionic bonding. It's also how we figure out the formula if we know the name of the compound. Another way to represent ionic bonding is to use the electron dot model. Here we draw the electron dot structure for sodium. Notice it has 1 dot because sodium is from the column where there's 1 valence electron. You can see that in red. And chlorine will have 7 dots. It's from the column where there will be 7 valence electrons. So we move the 1 electron over to chlorine to pair it up with the single electron on chlorine, and we get Na1 plus and Cl1 minus ions. Whenever you write electron dot models for ionic compounds, the positive ions should always end up with no dots, and the negative ions should always end up with 8 dots. Now remember that the reason that ionic bonding happens is because atoms are more stable when they have 8 valence electrons. They're more stable with an octet, or a group of 8 valence electrons. So here's an example of ionic bonding. Let's take a look at NaCl again, and let's take a look at the atoms before bonding. Notice that sodium, element number 11, would have 11 protons, and this would be its electron configuration. It has 11 electrons. That's what makes it neutral. Chlorine, element number 17, would have 17 protons, and because it's neutral, 17 electrons. That's before it bonds. When bonding happens, this single electron leaves the sodium and goes over to the chlorine. So what happens is we end up with Na1 plus because it now has 11 protons and 10 electrons, right? 1s2, 2s2, 2p6, that's 2, 4, and 6 more is 10 electrons. Notice it has an octet. Chlorine, which has 17 protons, becomes a 1 minus ion because now, once it gains the electron from sodium, it has 18 electrons. 1s2, 2s2, 2p6, 3s2, 3p6 is now its electron configuration. And notice that the electron configuration for this ion also has an octet. That's true of all stable ions. They will have an octet. That's why they're stable. Now, in ionic bonding, we say that the positive ion attracts the negative ion and vice versa because opposites attract. Ionic bonding is the strongest bond in general because both atoms, or I guess you could say both ions, have octets all of the time. Notice the sodium ion has an octet and the chloride ion has an octet. Now, we covered ionic bonding in some previous videos, and if any of what we've gone through so far is confusing or unfamiliar, you should watch those videos. Those are videos on ionic bonding. So let's take a look at covalent bonding. Covalent bonding happens when valence electrons are shared. We're sharing the valence electrons. That's why it's called covalent bonding. An example would be molecular chlorine, or the Cl2 molecule. Now, Cl2 is the chemical formula. What we can do to represent bonding is draw the electron dot structures for Cl and another Cl. And notice there are 7 valence electrons on each. And then we're going to connect, not use arrows, but rather connect the single dots. When we do that, the 2 electrons that are connected are represented with a dashed line. We can say that the bonding electron pair is represented as a dash between the atoms. That dash right here represents 2 electrons that are being shared between the atoms. Another way to represent it, and it's not very commonly done, is to just use 2 dots between the atoms. Now, if you want to, you can omit putting in the non-bonding electron pairs, but when you first begin to do these, you should really put the non-bonding electron pairs in. The bonding electron pair is shared, so that means it counts in the octets around both atoms in the bond. Let's make sure we have a valid structure. We started with 7 electrons and 7 electrons, so 14 electrons total around those 2 atoms. If we count the valence electrons here, we have 2, 4, 6. Remember, the bonding electrons are 2 electrons represented by that dashed line, so that's 2, 4, 6, 8, 10, 12, 14. We have all 7 and 7, 14 electrons represented here in this representation. This is called a 2-dimensional structural formula, or sometimes it's also called a Lewis structure, because Gilbert Lewis was the scientist that invented this method of using dot structures. So one of the things we want to do is make sure that we start and end with the same number of valence electrons. Make sure that all the valence electrons are accounted for when we connect the single electrons. Another thing we want to do is make sure that atoms have octets whenever possible as a result of covalent bonding. So if we take a look at this particular chlorine, we can see that it has an octet. And if we take a look at this particular chlorine, we can see that it has an octet. Again, notice that the bonding electrons, the electrons that are being shared, can count as part of the octet around both elements in the bond. So really what we're trying to do is make structures that have octets whenever possible and make sure that all the valence electrons are accounted for. Because, you know, the law of conservation of mass still holds true. We can't create electrons out of nowhere and make electrons disappear into nowhere. All right, so let's take a look at covalent bonding from the standpoint of electron configurations. Before bonding, we would have a chlorine and a chlorine, using that same example of Cl2, with 17 protons each, and 2, 4, 6 more is 10, 2 more is 12, and 5 more is 17. 17 electrons. Notice that each one of these is 1 electron short of having an octet. If we draw the electron dot structures for each atom, they would look like that. What happens when we share the electrons is that the 2 electrons in the bond are moving back and forth between these 2 atoms. So in one moment, we might see that this chlorine has 3s2, 3p6, or an octet. And this chlorine does not. It only has 3s2, 3p4 on the outside. But in another moment, the 2 electrons would switch over to this atom and be shared there. Now notice that at any one point in time, atoms in a bond only have an octet some of the time, right? This top chlorine would have an octet sometimes, and then when the 2 electrons switch down here, this bottom chlorine would have an octet. Now, if you take a view of the electron strictly as a particle, that's the way that you might look at that. And then it would make sense that covalent bonding is weaker than ionic bonding in general, because of the fact that while in ionic bonding, the ions involved have octets all of the time, in covalent bonding, the atoms that are involved in sharing the electrons, because the electrons are shared, only have electrons, an octet of electrons sometimes. Now, if you really want to take a more rigorously correct view that the electron is actually not just a particle, it's a wave particle, right? We studied some wave-particle duality leading up to this. The electron wave particle is more spread out when it's being shared between these 2 atoms. So when you spread out those valence electrons because they're shared, that means that there's less electron density between the nuclei, and that means the bond is a little bit less strong. So that's another way to look at it, a little bit more rigorously correct way to look at it with wave-particle duality in mind. In any case, covalent bonding is, in general, a little bit weaker than ionic bonding. Now that's a generalization, and there's always exceptions to that. All right, so covalent bonding can happen with a single bond where one pair of electrons is shared, with a double bond where two pairs of electrons are shared, or with a triple bond where three pairs of electrons are shared. You should take note that atoms do not share greater than 3 pairs of electrons, as there's too much electron-electron repulsion when we have all those electrons between the two nuclei. Remember, electrons are all negative and they do repel each other. So while the positive nuclei are pulling on the electrons are repelling each other. All right, so let's take a look at a single bond. This is where one pair of electrons are shared. We've already seen Cl2, and what we would do is draw the electron dot structures for Cl. Now remember that if you look at a periodic table, you can see that Cl should have 7 valence electrons, right? It ends with S2 P5. And it might not be a bad idea to just draw in the number of valence electrons on a periodic table like this periodic table on the ion sheet. So with 7 valence electrons, that's 7 dots each. We're going to connect the single electrons between the two atoms and then draw the structure of the chlorine molecule. And that's really the structure we have here. Kilomole just means little lump or little piece of this thing. So Cl bonds to Cl with that pair of electrons represented as a dash, and all the non-bonding electron pairs, the 6 electrons here and the 6 electrons here, are still represented. Here's another example of a single bond, a little bit more of a complex molecule, C2H6. That's an organic compound. It's a carbon-based compound. That's called ethane. So what we're going to do is connect the single dots. And I always like to start at the center, connect the single dots between the two atoms at the center, and then start connecting single atoms or atoms on the outside with single dots connecting to the inside. Because if they're part of the molecule and we have 6 hydrogens and 2 carbons, they do need to be connected somehow. So let's connect those single electrons to make bonds. And then let's clean that up a little bit and just draw those as dashes. And we can see we get this 2-dimensional structural formula. Again, this is the chemical formula. This is the 2-dimensional structural formula. It should be noted here that the hydrogens don't have octets. Notice that the carbon does. If we circle that one, and this carbon has an octet. But if we look at any one of the hydrogens, they don't. They only have 2 electrons to share. Now that's closer to an octet, and that is more stable. And every hydrogen would be the same way as this hydrogen. But elements in general from groups 1 and 2 and 13 are going to be exceptions to the octet rule. When we do covalent bonding, they just don't have enough electrons to share to get 8 electrons. Notice that sodium only has 1 electron, so when it shares it, and it's just like hydrogen, it would only get 2 from sharing. Beryllium, so we're looking at elements from this group, group 1, like hydrogen, and now beryllium from group 2 would have 2 valence electrons, or 2 dots. It could share this dot, and then that would give it 2 bonds, or 4 electrons around the nucleus, but that's not an octet. Group 13 elements, like boron, that's group 13 there, right? Groups 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Group 13 would have 3 valence electrons. Elements here end with S1, S2, P1, so S2P1, 3 dots. Sharing those dots would give it 6 valence electrons from bonding. That's still not an octet. So it should be noted that those elements will violate the octet rule. They're just not big enough. All right, so let's do some more connecting single dots here and show how that works with double bonds. A double bond is when 2 pairs of electrons are shared. So in the O2 molecule, oxygen has 6 valence electrons, and we have 2 oxygens, right? Oxygen is here with 6 valence electrons, so 6 dots. We can connect these 2 single dots and then connect these 2 single dots. We're going to put all of those connected dots between the two atoms because those are shared electrons. And you can see we started with 6 electrons and 6 electrons, so 12 electrons total. And here we have 2, 4, 6, 8, 10, 12 electrons represented. So all the electrons are represented. And if we look around this left-hand oxygen, we can see an octet, 2, 4, 6, 8. Remember, the dashed lines are each 2 electrons being shared. So that dashed line is 2 electrons, and that dashed line is 2 more electrons. That's 2 pairs of electrons. Notice that the shared electrons count both ways, so both oxygens have an octet, 2, 4, 6, 8, 2, 4, 6, 8. Here's another example of double bonding, C2H4. This is another carbon-based compound. If we connect the central atoms by connecting single dots, then connect the center atoms to the outside with connecting single dots, can do that. And notice that there are still a couple of electrons between those central atoms that are not connected. So let's connect those. And what we can see is now we have 2 pairs of electrons being shared, so 2 dashed lines here. Once again, we count up the octets around this carbon. We can see there's 2, 4, 6, 8 electrons. Same thing around this carbon. And notice that the hydrogens are each going to violate the octet rule. They come from group 1. They don't have enough electrons to share to get an octet, and all the hydrogens are the same. Now we started with 1, 2, and 4 from that carbon is 6, and 4 from that carbon is 10, 11, 12 electrons. We have 2, 4, 6, 8, 10, 12 electrons represented. So a double bond is when 2 pairs of electrons are being shared. Let's take a look at how triple bond works. For a triple bonding, one example is N3. A triple bond is where 3 pairs of electrons are shared. So we have nitrogen and nitrogen. Each will have 5 valence electrons. We can see that there in that group where all the elements in that group have 5 valence electrons. So we put our 5 dots in. Let's connect the dots here and here and here. And that's 3 pairs of dots connected, so 3 dashed lines. Notice that we started with 5 and 5 more, 5 dots and 5 dots. That's 10 electrons represented. And here we have 2, 4, 6, 8, 10 valence electrons represented. All the electrons are accounted for. Notice that around this nitrogen, there's an octet, 2, 4, 6, 8. And around this nitrogen, there's an octet, 2, 4, 6, 8. Here's another example, C2H2. Connect the central atoms. Connect the center atom to the outside on both sides of the molecule. Then connect any single electrons that are still there between the central atoms. So we get a triple bond between the 2 carbons, a single bond to that hydrogen, and a single bond to that hydrogen. Notice that around this carbon there are 2, 4, 6, 8 electrons. Around this carbon there are 2, 4, 6, 8 electrons. Remember, the bonding electrons count both ways. The hydrogen won't have an octet because it's from group 1, the same thing for that hydrogen. We started with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons, and we have 2, 4, 6, 8, 10 electrons represented. Now we're going to practice connecting the dots like this and making these 2-dimensional structural formulas. But that's not what I would like to focus on right now. What I'd like to focus on right now is just identifying the number of single, double, and triple bonds in each of the 2-dimensional structural formulas. If you understand what we went through in this video, you should be able to, looking at these structural formulas, identify the number of single, double, and triple bonds that exist in each molecule. And here's an example with this molecule, and we just went through it. We can see there's 1 triple bond and 1, 2 single bonds. Good luck.